So, welcome to our presentation of the Nand2Tetris Course. This is a course by Noam Nisan and Shimon Shakin. I'm Alex Walkoff.
I'm Maya Stein.
I'm Maurice Korish.
I'm Elior Lerman.
And I'm Adam Hollander. Just to go over a few prerequisites before we go into the course. So first of all, it's designed as an introduction. The course is designed as an introduction to chip design, and this is kind of the job of electrical engineers, and it's not necessarily organizing the physical, locations of the different gates within a chip. It's kind of designing the circuitry and kind of preparing to move on to the next phase, which is getting it ready for manufacturing. Now, just in case any of you are not familiar, binary numbers are expressed as power 2 to the n to the power of n, as you can see in the left diagram. So for instance, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 4 is 2, 2 to the 2 is 4, and etc. And basically, whenever those values in that digit are set to 1, you're just going to add that to the overall sum, and that's how binary numbers are expressed in decimal. And then also just another brief concept, logic gates are basically these small or these relatively small, operators that take in two inputs, or actually one or more inputs, it depends on the gate. And basically, depending on what it is, it'll output a specific value depending on the inputs. And for instance, for this course, it is extremely important to know that NAND gates, which are universally able to construct other gates, which is the basis of this course, how we're only given a NAND gate to start. And basically, they're the inverse of an AND gate, and they output ones no matter what, unless the A input and the B input are both ones, which is the exact opposite of an AND gate.
So Unit 1 discusses primitive gates, and you could write the code for each of the gates except for the NAND gate, which is given, as Adam referenced. And the computers are composed of zeros and ones, which these gates account for. They find ways to bring use to these zeros and ones and make up a computer. Some examples are the NOT gate, the AND gate, the OR gate, and then the XOR gate, which is shown. In the XOR gate, it's made up of NOT gates, AND gates, and an OR gate. And the way it works is it's going to output 1 if it gets a 0 and a 1, or it will output 0 if it gets 2 zeros or 2 ones.
Okay, so in Unit 2, that's the Boolean arithmetic in the ALU. So something you should understand before we get into all these, the 5 chips, is how to do basic mathematics addition with binary numbers. So if you look at that, small math problem, that's binary. It's not decimal. It's not 110. That's 110. And you'd start looking all the way on the right, and you will do it the same way you would do it in decimal. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 would be 1 0 in binary. So what you do is you take the 0, and then the leftover 1 would be the carry bit. So that's very important for the half adder and adders. You would have a carry bit. So in the half adder, you put in two different numbers, and then it'll give you a sum and a carry. And as you can look in the bottom, you would kind of understand for 1 1, your sum would be 0, your carry would be 1. Well, everywhere else, your sum is either zeros or ones, while your carries are all zeros. So then you move on to the full adder, which, without giving too much away, is you would add A and B, and then you have to take into account your carries and sum from A and B, and then add it with C. And then you would get a new sum and carry. So then there's the add 16, which this might look confusing, but all that means is it's a 16-bit binary number, and then you get a second binary number, and all you're doing is what I showed you before. You're just going to start going right to left and start adding them together the same way you do it in decimal, and you keep carrying. And once you make it all the way to the left, that last carry bit no longer matters. So you just forget about it. Then there's the INC16, which is now you take one 16-bit number, and all you're doing is adding 1, and you will do all the carries you need to do if there's any carries necessary, and that's how the INC16 works. Then there is the ALU. So with the ALU, you put in 2 inputs, the X and Y, and there are also a bunch of controls that you have to program. So you either put in a 1 or 0. So a quick example is the ZX. So if you put a 1 into the ZX, then it's going to set your X value that you put in to a 0. And the NX would take your X value and just inverse it. So if you look all the way on the right column, the out, those are all the different outcomes you can get using those commands, using these programs. And that's how the ALU works.
So now we will move on to memory now that we have our ALU, our arithmetic logic unit, constructed. So memory, as an overview, is quite straightforward conceptually, at least in terms of the name in this unit. It is the capability to store data, and the fundamental aspect of memory is the DFF data flip-flop. And this allows us to store binary values over sequential clock cycles. So as you see on the bottom right in this graphic, what's happening is the DFF enables us to output the value of the previous input. And just to give a brief and output that over consistent clock cycles. So just to give a brief understanding of the clock, every computer device has an internal clock that essentially maintains a consistent rhythm for executing code or executing some sort of machine language, which will be touched upon later in this presentation. So in this example, the DFF, what it does is it takes in an input, for example, in clock cycle 1, and that input is then outputted in clock cycle 2. And that's how we see this angular shape of the lines, because the previous input is what's being outputted in the following clock cycle. So this already begins building the foundation for storing values, particularly binary values, a 0 or a 1 in this case. So for example, if we have an input of a 1 in clock cycle 1, then the output in clock cycle 2 will simply be that 1, or f of a. And in this case, a would be clock cycle 1, and then clock cycle 2 would be b, and then f of b would be the output of clock cycle c, or 3. Because that's the previous one. So now you can see that this begins to develop a basic method of storing values from previous clock cycles. And then this will enable us to store values in higher levels of memory, such as the RAM and registers, which we will get into on the next slide. So higher levels of memory are first built on registers, and then registers are what make up the RAM, and the RAM is also known as the random access memory. So with one DFF, we can move on to develop a 1-bit register, and then this process is simply increased by varying factors until, in our case, we've reached a total of 16K registers, which is what we built for our emulated computer in this course. And just to expand upon that a bit, all of the registers, so with one DFF, we can build a 1-bit register, but our computer was a 16-bit computer. So that means that we don't want a 1-bit register. We want our registers to have 16 bits or be able to store 16 bits. So this was simply expanded upon 16 times. And then we developed a method for storing 16-bit values within one register. So now that we have a 16-bit register, we could put 8 of them into one stored unit to develop the RAM 8, which the RAM 8 is pretty self-explanatory. It has 8 registers, and all of those registers have the capability to store 16-bit values. And then this is expanded upon so forth with the 64, with the RAM 64, which has 8 RAM 8s. And then this is the sequential process of abstraction. And we continue to expand, of course, to the RAM 512, and of course, then to the RAM 4K and the RAM 16K. And I would just like to point something out here, that while this is simply a 16-bit computer, computers nowadays are usually 64 bits and potentially even 128 bits. So this is just to give a bit of perspective. While this may seem like a lot of storage, it's really minuscule in comparison to how much a computer or a smart device such as an iPhone or an Android device may be able to store. And you begin to understand the value of memory and storage within computer devices.
So now that we've kind of discussed the many components that you find in common computers, I'll now go into machine language, which is kind of how all those components are coordinated together. So first of all, machine language is the most basic programming language possible, and it's directly translated into binary that's then used to control the various components. So and that process of transforming higher level programming languages such as C++ into machine language is called compiling. And as you can see in the diagram on the right, it's actually quite clever how binary is kind of used in order to encrypt functions. And basically, just really quickly, as you can see, the C computes the C segment of the binary number, computes using the ALU, or it can also perform logic operations. And the output of that logic operation is then stored in the destination defined by the D section. And there's also a jump section that I'll also touch upon later that has a lot of practical applications in terms of higher level programming. And now I'll continue onwards. And so basically, one key aspect of machine language is that it combines access and the ability to store values in registers with the operations of the ALU. And that kind of that creates a cohesive language that can then be built on by higher level languages such as Python, Java, JavaScript. And just one other important point about machine language is the ability to communicate and receive data from the user. For instance, on a laptop, that would include your mouse, your keyboard, your screen, and kind of coordinating all of those aspects is a key function of machine language. And just I'll touch on the jump point that I mentioned before, how a segment of the binary code is used to jump to different addresses, or I'm sorry, different instruction numbers within the program. And that, as you can imagine, would allow you to have if statements and a lot of other complex control flow applications. And this is actually on the bottom, we have a quick video, which is one of the projects that you'll complete in the machine language portion of the course. And as you can see, when the user presses down a button from the keyboard, the input, there's a corresponding output, and this is all done in machine language. It's a lot more difficult than it seems, but it's quite rewarding, and it demonstrates the capabilities and the applications of using machine language.
So the next unit is building the hat computer. So in modules 1 through 3, units 1 through 3, what you did is you designed the basic chips necessary to run a computer in the first place. So the adds, the increments, the multiplexers, the demultiplexers. And then in Unit 4, you took a pre-built software computer, which is the CPU emulator, and you wrote 2 programs for it. So the fill, which is what Adam showed, and you also built the multiplier. Now, in Unit 5, you go back and take all of the different chips that you made and combine them into one computer. And the primary part of this computer is the CPU. And the way a CPU works is it uses what's called a fetch-execute cycle. So the CPU understands a set of instructions that come from the memory, and then it executes them. So each action takes 3 steps. It fetches the instructions, it decodes the instructions into binary from the machine language, and then executes them. And then it will do that from the time it is turned on until the time it shuts down, which means there are no more instructions. And just an example of this, say you had a statement of code that was area equals length times width, length and width being variables, and area being the target variable. So what the computer would have to do is it would take 4 steps to do that. 4 steps times the 3 for the fetch execute cycle. So it fetches the length variable, sees that number, fetches the width variable and sees that number, multiplies them, and then attaches them to the area variable. And that is all part of the computer's architecture. Now, there are generally 2 different types of architecture, the von Neumann architecture and the Harvard architecture. The von Neumann architecture has a single channel, as you can see in the diagram, for data going back and forth, and choosing the address, sending the address from which to grab the instructions. Whereas the Harvard architecture has 2 channels, one for sending the address of the instructions, and another for getting the instructions that are at that specific place. And while you might think initially that having the 2 channels is better because it's faster, it's a lot less flexible and it's a lot more bulky. Because when you have 2 channels, that means that there are fewer resources for the rest of the computer to use, such as your graphics card, which is complicated, and your mouse, your keyboard, and all of that. So that's a lot less flexible. Whereas the von Neumann machine, it might be slower because only one thing can go through at a time, but it takes a lot less to apply the von Neumann architecture. So in the computers that we are all giving this presentation on, that uses von Neumann architecture because common computers have a lot of applications and a lot of uses. And they need to be able to use lots of different resources at the same time, even though it might not be as fast. Whereas, say, your washing machine only has one application, only one purpose, and so it can use the Harvard architecture because all it cares about is speed. Flexibility isn't necessary. Thank you for listening to this presentation, and I hope you learn a lot during the course just like we did.